Chapter 7. Project, a Robot. The question of whether machines can think is about as relevant as the question of whether submarines can swim. Edgar Dijkstra, The Threats to Computer Science. In project chapters, I'll stop pummeling you with new theory for a brief moment, and instead we can work through a program together. Theory is necessary to learn to program, but reading and understanding actual programs is just as important. Our project in this chapter is to build an automaton, a little program that performs a task in a virtual world. Our automaton will be a mail delivery robot picking up and dropping off parcels. Meadowfield. The village of Meadowfield isn't very big. It consists of 11 places with 14 roads between them. It can be described with this array of roads. The network of roads in the village form a graph. A graph is a collection of points, places in the village, with lines between them, roads. This graph will be the world that our robot moves through. The array of strings isn't very easy to work with. What we're interested in is the destinations that we can reach from a given place. Let's convert the list of roads to a data structure that, for each place, tells us what can be reached from there. Given an array of edges, buildGraph creates a map object that, for each node, stores an array of connected nodes. It uses the split method to go from the road strings, which have the form start, end, to two-element arrays containing the start and end as separate strings. The task. Our robot will be moving around the village. There are parcels in various places, each addressed to some other place. The robot picks up parcels when it comes across them and delivers them when it arrives at their destinations. The automaton must decide at each point where to go next. It has finished its task when all parcels have been delivered. To be able to simulate this process, we must define a virtual world that can describe it. This model tells us where the robot is and where the parcels are. When the robot has decided to move somewhere, we need to update the model to reflect the new situation. If you're thinking in terms of object-oriented programming, your first input might be to start defining objects for the various elements in the world. A class for the robot, one for a parcel, maybe one for places. This could then hold properties that describe their current state, such as the pile of parcels at a location, which we could change when updating the world. This is wrong. At least it usually is. The fact that something sounds like an object does not automatically mean that it should be an object in your program. Reflexively writing classes for every concept in your application tends to leave you with a collection of interconnected objects that have their own internal changing state. Such programs are often hard to understand and thus easy to break. Instead, let's condense the village's state down to the minimal set of values that define it. There's the robot's current location and the collection of undelivered parcels, each of which has a current location and a destination address. That's it. While we're at it, let's make it so that we don't change a state when the robot moves, but rather compute a new state for the situation after the move. The move method is where the action happens. It first checks whether there's a road going from the current place to the destination, and if not, it returns the old state since there is not a valid move. Next, the method creates a new state with the destination as the robot's new place. It also needs to create a new set of parcels. Parcels that the robot is carrying that are of the robot's current place need to be moved along to the new place, and parcels that are addressed to the new place need to be delivered. That is, they need to be removed from the set of undelivered parcels. The call to map takes care of the moving, and the call to filter does the delivering. Parcel objects aren't changed when they're moved, but recreated. The move method gives us a new village state, but leaves the old one entirely intact. The move causes the parcel to be delivered, which is reflected in the next state. But the initial state still describes a situation where the robot is at the post office and the parcel is undelivered. Persistent data. Data structures that don't change are called immutable or persistent. They behave a lot like strings and numbers in that they are who they are and stay that way rather than containing different things at different times. In JavaScript, just about everything can be changed, so working with values that are supposed to be persistent requires some restraint. There is a function called object.freeze that changes an object so that writing to its properties is ignored. You could use that to make sure your objects aren't changed if you want to be careful. Freezing does require the computer to do some extra work, and having updates ignored is just about as likely to confuse someone as having them do the wrong thing. I usually prefer just to tell people that a given object shouldn't be messed with and hope they remember it. Why am I going out of my way not to change objects when the language is obviously expecting me to? Because it helps me understand my programs. This is about complexity management again. When the objects in my system are fixed, stable things, I can consider operations on them in isolation. Moving to Alice's house from a given start state always produces the same new state. When objects change over time, that adds a whole new dimension of complexity to this kind of reasoning. For a small system like the one we're building in this chapter, we could handle that extra bit of complexity. But the most important limit on what kind of systems we can build is how much we can understand. Anything that makes your code easier to understand makes it possible to build a more ambitious system. Unfortunately, although understanding a system built on persistent data structures is easier, designing one, especially when your programming language isn't helping, can be a little harder. We'll look for opportunities to use persistent data structures in this book, but we'll also be using changeable ones. Simulation. A delivery robot looks at the world and decides in which direction it wants to move. So we could say that a robot is a function that calls a village state object and returns the name of a nearby place. Because we want robots to be able to remember things so they can make and execute plans, we also pass them their memory and allow them to return a new memory. Thus, the thing a robot returns is an object containing both the direction it wants to move in and the memory value that will be given back to it the next time it is called. Consider what a robot has to do to solve a given state. It must pick up all parcels by visiting every location that has a parcel, and deliver them by visiting every location to which a parcel is addressed, but only after picking up the parcel. What is the dumbest strategy that could possibly work? The robot could just walk in a random direction every turn. That means with great likelihood it will eventually run into all parcels, and then at some point reach the place where they should be delivered. Here's what that could look like. Remember that math.random returns a number between 0 and 1, but always below 1. Multiplying such a number by the length of an array and then applying math.floor to it gives a random index for the array. Since this robot does not need to remember anything, it ignores its second argument. Remember that JavaScript functions can be called with extra arguments without ill effects, and omits the memory property in its returned object. To put this sophisticated robot to work, we'll first need a way to create a new state with some parcels. A static method, written here by directly adding a property to the constructor, is a good place to put that functionality. We don't want any parcels to be sent from the same place that they are addressed to. For this reason, the do loop keeps picking new places when it gets one that's equal to the address. Let's start up a virtual world. It takes the robot a lot of turns to deliver the parcels because it isn't planning ahead very well. We'll address that soon. For a more pleasant perspective on the simulation, you can use the run robot animation function that's available in this chapter's programming environment. This runs the simulation, but instead of outputting text, it shows you the robot moving around the village map. The way run robot animation is implemented will remain a mystery for now, but after you've read the later chapters of the book, which discuss JavaScript integration in web browsers, you'll be able to guess how it works. The mail truck's route. We should be able to do a lot better than the random robot. An easy improvement would be to take a hint from the way real-world mail delivery works. If we find a route that passes all places in the village, the robot could run that route twice, at which point it's guaranteed to be done. Here's one such route starting from the post office. To implement the route following robot, we'll need to make use of robot memory. The robot keeps the rest of its route in its memory and drops the first element every turn. This robot is a lot faster already. It'll take a maximum of 26 turns, twice the 13-step route, but usually less. Pathfinding. Still, I wouldn't really call blindly following a fixed route intelligent behavior. The robot could work more efficiently if it adjusted its behavior to the actual work that needs to be done. To do that, it has to be able to deliberately move toward a given parcel or towards a location where a parcel has to be delivered. Doing that, even when the goal is more than one move away, will require some kind of route finding function. The problem of finding a route through a graph is a typical search problem. We can tell whether a given solution, a route, is valid, but we can't directly compute the solution the way we could for 2 plus 2. Instead, we have to keep creating potential solutions until we find one that works. The number of possible routes through a graph is infinite, but when searching for a route from A to B, we are interested only in the ones that start at A. We also don't care about routes that visit the same place twice. Those are definitely not the most efficient route anywhere. So that cuts down on the number of routes that the route finder has to consider. In fact, since we are mostly interested in the shortest route, we want to make sure we look at short routes before we look at the longer ones. A good approach would be to grow routes from the starting point, exploring every reachable place that hasn't been visited yet until a route reaches the goal. That way we'll explore only routes that are potentially interesting, and we know that the first route we find is the shortest route, or one of the shortest routes if there are more than one. Here's a function that does this. The exploring has to be done in the right order. The places that were reached first have to be explored first. We can't immediately explore a place as soon as we reach it because that would mean places reached from there would also be explored immediately and so on, even though there may be other shorter paths that haven't yet been explored. Therefore, the function keeps a work list. This is an array of places that should be explored next, along with the route that got us there. It starts with just the start position and an empty route. The search then operates by taking the next item in the list and exploring that, which means it looks at all roads going from that place. If one of them is the goal, a finished route can be returned. Otherwise, if we haven't looked at this place before, a new item is added to the list. If we have looked at it before, since we are looking at short routes first, we've found either a longer route to that place or one precisely as long as the existing one, and we don't need to explore it. You can visualize this as a web of known routes crawling out from the start location, growing evenly on all sides, but never tangling back to itself. As soon as the first thread reaches the goal location, that thread is traced back to the start, giving us our route. Our code doesn't handle the situation where there are no more work items in the list, because we know that our graph is connected, meaning that every location can be reached from all the other locations. We'll always be able to find a route between two paths, and the search can't fail. This robot uses its memory location as a list of directions to move in, just like the route following robot. Whenever that list is empty, it has to figure out what to do next. It takes the first undelivered parcel in the set, and if that parcel hasn't been picked up yet, plots a route toward it. If the parcel has been picked up, it still needs to be delivered, so the robot creates a route toward the delivery address instead. Let's see how it does. This robot usually finishes the task of delivering five parcels in about 16 turns. That's slightly better than Route Robot, but still definitely not optimal. We'll continue refining it in the exercises. Exercising. Measuring a robot. It's hard to objectively compare robots by just letting them solve a few scenarios. Maybe one robot just happened to get easier tasks or the kind of tasks that it's good at, whereas the other didn't. Write a function, compare robots, that takes two robots and their starting memory. It should generate 100 tasks and let both of the robots solve each of these tasks. When done, it should output the average number of steps each robot took per task. For the sake of fairness, make sure you give each task to both robots rather than generating different tasks per robot. Robot efficiency. Can you write a robot that finishes a delivery task faster than goal-oriented robot? If you observe that robot's behavior, what obviously stupid things does it do? How could those be improved? If you solve the previous exercise, you might want to use your compare robots function to verify whether you improve the robot. Persistent group. Most data structures provide a standard JavaScript environment aren't very well suited for persistent use. Arrays have slice and concat methods which allow us to easily create new arrays without damaging the old one. But set, for example, has no methods for creating a new set when an item added or removed. Write a new class, pgroup, similar to the group class from chapter 6, which stores a set of values. Like group, it has add, delete, and has methods. Its add method, however, should return a new pgroup instance with the given member added and leave the old one unchanged. Similarly, delete should create a new instance without a given member. The class should work for a value of any type, not just strings. It does not have to be efficient when used with large numbers of values. The constructor shouldn't be part of the class's interface, though you'll definitely want to use it internally. Instead, there's an empty instance pgroup.empty that can be used as a starting value. Why do you need only one pgroup.empty value rather than having a function that creates a new empty map every time?